Kieran Koto. It's really nice to be here. Thank you, Jody, because Jody covered a lot of things that now I don't have to. But I'm also going to try to make this science light, but not science free. But if I get that line wrong, just let me know, okay? My purpose here tonight is to talk about, in general, antibiotic resistance, and specifically the connection between antibiotic resistance and chemical exposures for the microbiota, yours, your pets, or soil microorganisms. I really want to first acknowledge the cast and crew that I work with at the university who have helped make the story I'm going to tell you tonight possible. Okay, Yanni. So I've been playing in the Avon River a bit, and a few other rivers around the place. And you won't be surprised to know there's lots of E. coli there. And E. coli is a great indicator of human contamination because E. coli lives in our gut. A big component of your poo is E. coli. So when we find E. coli in waterways, we know it comes from things like mammals, people, and birds. Well, we've done several years of study on the Avon right here in Hagley Park. And on the left, what you see here is mesophiles. This is a just general survey of bacterial counts. Every place has bacteria. Bacteria are wonderful. You're full of them, and you're wonderful. So by association, we know everything's good. When they get out of their place, though, things can go wrong. Now you start to see in the next set over the counts for E. coli. And those counts are way, way, way above the recreational safe water swimming limits. Then what we do is we say, how many of those E. coli are resistant to antibiotics? So ampicillin, ciprofloxacin, chlorphenicol are antibiotics. And you can see a large proportion of the E. coli in the Avon River is resistant to antibiotics. The frequency of resistance is so high that most of those that are resistant to an antibiotic are resistant to 3, 4, 5, 6 different antibiotics all at once, including for E. coli, the 2 or 3 most important clinical first resort drugs, such as ciprofloxacin. This graph here is showing you just the names of isolates on the left, and the little squares correspond with what that isolate, the antibiotic to which that isolate is resistant. And we do a panel of 1, 2, 3, 4, 5, 6, 7, 8, 9 different antibiotics. The latest generation penicillin-type drugs, the cephalosporins, as well as ciprofloxacin and the immunoglycosides that your clinician would use, but also chlorphenicol and tetracycline, which would be important for your pets. The darkness of the square tells you the concentration of the antibiotic that was necessary to kill that isolate. And the darker it gets, the higher the concentration. What I want to tell you is that the very lightest color you can see is, generally speaking, the clinical breakpoint concentration. That means that everybody who has a square is no longer treatable in the clinic. These are taking on the characteristics of bacteria who can't be treated with antibiotics if you were to get an infection from them. Ciprofloxacin is of particular interest to me because this is a drug that doesn't exist in nature. It's not a natural antimicrobial. It's completely synthesized by people. So we would have expected resistance to a drug like ciprofloxacin to have arisen much more slowly because there wasn't already experience of this compound amongst the bacterial community. On the Avon River and also rural streams around Christchurch, we're getting ciprofloxacin to resistance to 32 times the clinical breakpoint. So these are huge levels of resistance. Interestingly, when ciprofloxacin first came out, people tried to see if they could get resistance. In the laboratory, it's almost impossible to get high-level resistance to ciprofloxacin. Jody was telling you that we have a chemically intensive world. Lots of different chemicals. Lots of things in commerce that haven't been in commerce prior to World War II, despite our many hundreds of thousands of years of evolution. But it's also an interactive world. So things are coming together in ways that they didn't before. One of those interactions is between pesticides and antibiotics. So on the right you see just a Guardian article from about a year ago talking about how you can routinely detect both in waterways in Europe, antibiotics and pesticides. The same is true here. Pesticide use is one of the largest dispersals of a human-made chemical in the world. So we use it everywhere. We use it in urban settings as well as rural settings. Even though often we think of these as agricultural compounds, they are ubiquitous in our experience. Glyphosate-based herbicides are the number one by far. So the world uses more glyphosate-based herbicides than any other kind of herbicide. And we use it in many different places. Jody went through that, both urban and agricultural, on your food, and for reasons that have nothing to do specifically with weed control when we use it as a desiccant. And we have equally complex exposure pathways to these kinds of compounds. So here's an old newspaper article from Stuff. A woman who takes her dog to the park was upset because her dog was running through the park that had just been sprayed with Roundup. But she didn't know it had been sprayed with Roundup. And this can be happening all the time for two reasons. One, they tell you it's not toxic, so there's very little regulation on their use. But two, the label tells you you can do that. So if you buy a bottle of Roundup, and it'll say that, well, you can spray this on your paddock. Say you're a dairy farm. You can spray this on your paddock. And if you want to, you can just let the cows go out and eat that grass. Right then and there, there's no stand-down period. Now, the label recommends that you wait 3 days because it takes 3 days for the glyphosate to get into the plant and kill it. And if you let the cow eat it too soon, then the plant will grow back. But it's not because of a human health or animal health issue. It is because you're defeating the product. So we're given many signals to say that it's okay. Now, your pets run through the park. Your children run through the park. As Jody was saying, these pets are kind of low to the ground. They're like me, pretty close to the ground. So that's how I get a lot of empathy for this topic. And these pets are on antibiotics sometimes. On the right is a list of the different kinds of veterinary-approved antibiotics that dog could be on. So now we have sort of the perfect storm. We have exposures to the herbicides and to antibiotics at the same time. That's a picture of my foot. That's not a picture of my feces. But, and it's not necessarily from that dog, but it's from a dog. And you can see it's only a few centimeters from the river. So this is the pathway now back to our waterways, from the park to the waterway, or from our shoes to our homes, from our pets' feet to our homes, from our litter box to the air. So here's a picture of what happens when antibiotics and pesticides come together. Now this picture is taken for the herbicide dicamba, but it could have been with any of those big three, dicamba, 2,4-D, or glyphosate-based active ingredients. In the upper left-hand corner, we're just counting the number of bacteria. And the 9 on the bottom of that plate means that the dilution factor is 1 billion. So in the starting tube, there are 1 billion bacteria per milliliter. At the 10 to the 3 spot, there would have been 1 million bacteria that we put on the plate. So that's the range of the dilutions. No antibiotic, no herbicide, upper left-hand corner. If we put antibiotic into that media, there's nothing. It's clear. all of them are dead. At the highest concentration of 1 million, 0 live. It's a good antibiotic. If we put herbicide into that plate, we get the same number of bacteria. It's a little harder to see, but the same number of bacteria as on the plate above. We still get 1 billion per mil, and there's 1 million up there in the 10 to the 3 spot. If we put the herbicide and the antibiotic together, 100% of the bacteria live. So before, I told you, we're killing 1 million of them in that one spot alone, and here, all of them live. When they're put on the plate, they're one cell. You can't see one bacterium. So they grow into a colony, and that's what you're seeing here. The colony is approaching on the order of 1 billion bacteria. So the combination of the herbicide and the antibiotic has allowed 50 generations of growth from the cell to the colony. 50 generations for the possibility, new mutations, new traits, and all the other kinds of things bacteria get up to. No pre-exposure to the herbicide was necessary. The herbicide is so fundamentally and quickly protective that it saves the bacteria even faster than the antibiotic can kill the bacteria. And then they become immune to the antibiotic. Now we see a variety of different effects. Sometimes, here's an example of 3 herbicides. Dicamba, 2,4-D, Roundup is our glyphosate base. Sometimes what we find for some species of bacteria are combinations of herbicide and antibiotic where the antibiotic becomes less effective. That's an upward arrow. And sometimes we see that the herbicide makes the bacterium more susceptible. That is, it takes less antibiotic to kill them. That's the down arrow. And I know what you're thinking. And there are a few cups back there, but I don't recommend you drink the herbicide just because you're already on an antibiotic. Okay? Because regardless of whether the arrow goes up or down, the bacteria evolve resistance to that antibiotic much faster. Now the size of these arrows, measured in the change in the concentration of the antibiotic necessary to kill the bacteria, is up to 300%. As little as a 2-fold change can undermine the clinical effectiveness of an antibiotic for 75% of patients. And we're talking only a 2-fold change. Here they can be up to a 300% change. And it's not just the active ingredient. One of the things Jody was talking about was formulations. And one of the ways in which regulators can disagree with things like the IARC is because regulators will only look at studies that involve active ingredients. But nobody here buys an active ingredient. You buy a commercial formulation. And the commercial formulations are made up of other things than the active ingredient as well. For herbicides, these are things that we call surfactants and wetting agents. We found that very common surfactants also cause antibiotic resistance, separately from the active ingredient. So now you have multiple chemical inputs in these formulations, all of which can contribute to the same phenomenon. Protective, ultimately, for antibiotics. And the effect is in the same range, 0 to 300%. And before everybody gets so high and mighty about herbicides, let me just tell you a little story. These surfactants are, in food production, called emulsifiers. They're the same chemicals. So when you eat a Twinkie, or mayonnaise, or ice cream, you're also eating the same thing that are used as surfactants and herbicides, and they cause this effect. This is a busy graph, but let me just tell you the lesson. What we're measuring here is the lowest concentration of the herbicide to cause antibiotic resistance or a change in the susceptibility to an antibiotic. So as you go from left to right, the concentration of the herbicide increases, And the size of the bar is the change in that concentration response to the antibiotic. Every one of those concentrations is below the label recommended application rate. So that woman's dog was running through something that was relevant to the bacteria. Some of those numbers are below the maximum residue limits for animal feed, and some of those numbers are right on the border of the human maximum residue limits. So as an example of what happens, the phenomenon we first discovered is called an adaptive phenomenon. That is, the bacteria encounter a herbicide and an antibiotic. And what we think happens, and we've done some genetics, we've done some biochemistry to support this hypothesis, what we think happens is that the bacteria see the herbicide as a toxin. Remember, herbicides are meant to kill plants. And for the most part, these herbicides are really bad toxins for bacteria. They're not that toxic. Glyphosate, as an active ingredient in Roundup in general, is the most toxic to bacteria of the herbicides we've tested, but even it's pretty bad. Okay? This is not what you want to take to cure that gastrointestinal or urinary tract infection. You do want the antibiotic. But the bacteria don't know this, and they turn on their defenses to the herbicide. Those defenses are generic enough that they also change the susceptibility to the antibiotic at the same time. The mystery is how they do that so fast, but nevertheless, this is what happens. When you take the herbicide away, after a couple of generations, the bacteria have shut off the genes that they had turned on because of the herbicide, and they go back to their original phenotype, whatever that was, of susceptibility. But what I told you is that under the conditions where both the herbicide and the antibiotic are around, they grow many more generations than they would have, which gives them a chance to mutate. So we've measured the frequency at which now they mutate to antibiotic resistance. And this is the kind of resistance that doesn't go away after a couple generations. It stays. Here's one example. Roundup with the antibiotic ciprofloxacin. Remember the frontline clinical antibiotic for urinary tract infections for E. coli? Where you get infected, say, by swimming? We measure the frequency of spontaneous ciprofloxacin resistance with the herbicide and with the herbicide and ciprofloxacin. Now, we don't measure it with just ciprofloxacin because they'd all be dead. They are all dead at that concentration of ciprofloxacin. But when you put the two together, you get ciprofloxacin, high level ciprofloxacin resistance 100,000 times faster than you would without the herbicide. Everybody loves bees. In particular, I'm taken by our native pollinators, so the non-hive, non-honeybee type, but I'm not here to judge, so if you have other interests, that's okay too. A couple of years ago, a paper came out saying glyphosate residues in crops were altering the honeybee gut microbiota, and because different bacteria have different susceptibilities to Roundup, the Roundup was killing some species, but not killing others. Unfortunately for the bees, the species that were more resistant to Roundup were also the ones that cause disease in bees, such as Serratia marcescens. So Roundup favors bee pathogens. Well, we wondered whether it also could predispose those pathogens to antibiotic resistance, because in many countries, including New Zealand, honeybee hives are prophylactically treated with antibiotics because bees are sick. This is just an example with Roundup and two different antibiotics, ciprofloxacin and streptomycin. And what you see is a huge increase in the amount of antibiotic Serratia marcescens can now tolerate because of its exposure to Roundup. So the red bars show you, without herbicide, how quickly the bacteria die at the antibiotic concentration on the x-axis. The blue bars tell you how well they live. So 100% of our population is still living at 8 micrograms per mil, which is 16 times the clinical breakpoint concentration for ciprofloxacin. And 100% of them are living at 64 micrograms per mil of our aminoglycoside. Human exposure pathways are equally complex. There are many different ways in which we encounter both antibiotics and herbicides. It may be spray drift, as you see in those 2 pictures in the upper left. It may be walking down the aisle of Mitre 10 or Bunnings. Because you ever walk down the gardening aisle? It's stinky. And it's stinky on purpose because some of these pesticides would be explosive, so they have to breathe. So the packaging is designed to let you breathe it. And you're getting, yeah, exactly, yeah. Maybe you have a kid or a puppy and they're playing in the lawn. Kids don't have the same boundaries with tongues that maybe you have. And certainly houseflies and blowflies don't have any kind of problem with, poop. And they can fly from a paddock or from a park onto your coffee cup. So you have pathways not just of these residues, you have pathways for the microbes that have previously been exposed to these different environmental conditions. They can come back to you. So my take-home messages still emphasize our problem is antibiotic resistance. And antibiotic resistance is caused by our use of antibiotics, overwhelmingly. The question is, though, if we stopped using antibiotics, would we have antibiotic susceptibility? And here the question becomes much more complex. Because if lower and lower concentrations of antibiotic still select for resistance in the presence of things like these herbicides, it could take a long, long time for our environment to be so clear of antibiotics that we would start to significantly reverse, the speed at which different pathogens are becoming resistant to our antibiotics. So combating antibiotic resistance, which is not the same thing as worrying about the evolution of antibiotic resistance, combating it may require far more sophisticated thinking than we've applied to how it evolved in the first place. We may have to think about our chemical exposome for our microbes if we're going to have a serious chance of arresting future evolution of resistance, especially to new drugs that we haven't used yet. Because it would be a real shame to introduce a new antibiotic only to have it become obsolete within a few years because we haven't done our homework to introduce it into an environment where it will remain effective for generations to come. The lesson with antibiotic resistance is, once resistance evolves, the second time, no matter how long ago you stopped using it, the second time you use that drug, it comes back really fast. So it's one of those kinds of resources that is non-renewable. You use it, and you try to use it for as long as you can, but under conditions that retain its use if it's going to be for you and future generations. And we don't know how many different kinds of chemical mixtures cause the effects I'm telling you about. But I do have some good news. We have tested some different kinds of chemicals, even of similar class, that don't seem to have these effects. So it's not impossible to think of a future manufacturing policy that used different chemical surfactants and wetting agents and possibly active ingredients that didn't cause antibiotic resistance. If there was a will, and of course to have the will, first people have to realize that there's a reason to want to use these different agents and to do research on those. I'm not a chemist. Andy's a chemist, so he can do that work. I'm not pitching for it. Okay? But one thing I will pitch is that you've heard some scary things about glyphosate, and there's good reason to be concerned with these herbicides and other kinds of pesticides. But one thing we shouldn't do is rush into new solutions, new promises of herbicides and insecticides that are going to be magically, perfectly non-toxic. And of those classes are nucleic acid-based formulations that are going to be on the market as early as next year, and which our Environmental Protection Agency has proactively deregulated without a test. So we've challenged that decision in a series of peer-reviewed publications. I'm leaving some copies here. I'm just forewarning you that not every technological solution to a technological problem is a new pot of gold. Thank you very much.